Welcome. In this session, we'll explore the geometry of KKT points for an optimization problem that has two linear inequalities. We'll look at this problem. It will be a quadratic objective, and then you don't have to make note of these yet. We'll have two inequality constraints. In this case, our objective function is not simply a squared norm. So let's write down that objective function, and we'll refer to this later. So that is, we square the first entry and then we add 4 times the second entry, and we'll consider each of these constraints as a separate problem, and then we'll put them together. This illustrates the contours of the objective function that we're looking at. So now let's look at our problem number 5. And problem 5 is this objective function, and property 5 is 0, 1 times the argument plus 2 is less than or equal to 0. And that reduces to the second entry has to be less than or equal to minus 2. And we can see immediately that a solution to this unconstrained problem, a minimizer, in fact the global minimizer, is at the origin. It's at 0. And if we're constraining the second entry of the constrained minimizer to be less than or equal to minus 2, then this constraint will be active. If this constraint is active, then we know that the solution has to be a boundary point for the constraint, which means that it has to be an equality. And when we solve this as an equality, and we can use the primal or dual method, what we find is that the constrained solution, and we could even do this geometrically, is this will be, if we make the first entry bigger than 0 or less than 0, that will only increase this objective function, so that has to be a 0. And then we said that we want to treat this as an equality constraint, so when we set W2 equal to minus 2, that must be our solution. And when we compute the Lagrange multiplier for this problem, what we get is it's positive, and it's plus 16. Let's take a look at the geometry of this problem. When we generate a plot of this, what we see is that this shaded region is the feasible set, and if a point was an interior point of this feasible set, it wouldn't have a contour for the objective function that was as small as if it was the boundary. And from this geometry, we can see that if we increase or decrease that first entry of the argument, that would increase the level of the objective function, and so this geometrically has to be the solution. So this first constraint was simple. Now let's add the second constraint. When we look only at the second constraint, that leads us to problem 6. And problem 6 is this same objective function, and now property 6 of our vector argument was minus 1, 2 times W plus 5 has to be less than or equal to 0. And we could rewrite that. We could say that that's equivalent. That's equivalent to saying that minus W1 plus 2 times W2 is less than or equal to minus 5. And that, if we were to do some very simple plotting where this is W1 and this is W2, that would be an oblique region in this coordinate frame. So once again, if we take the unconstrained minimizer to 0, 0, and apply and put that into the property function, what we see is that this constraint would not be satisfied. So that means the constraint is active. If the constraint is active, then the solution is a boundary point on the constraint, and a boundary point means we set that to equal, and so we solve this using the primal or dual method, and what we get is a solution for problem number 6, which is 2.5 minus 1.25. And the implication of that is that when we solve that equality problem, our Lagrange multiplier is plus 5. Now, let's take a look at the geometry. The geometry of this problem is that this shaded region is the feasible set, and a point that's an interior point in this feasible set would not have an objective level that is as small as if it was on the boundary. So for this single constraint, the solution to the constraint optimization problem is a boundary point, and that's why we can solve it as an equality problem for just this one. So when we work this out, if we take any point that's along this boundary, this point here is the one that has the minimum objective level that we want. So now we've looked at each one of these two constraints independently. Let's combine the constraints. When we combine the constraints, we have problem 7. And problem 7 is this objective function, and we had the combined properties have to be both less than or equal to 0. So the solution has to be in the feasible set. When I work this out geometrically or numerically, what I get is that our number 7 problem is solved at 1 minus 2. Now let's take a look at this. The solution to property 5 only was 0 minus 2. The solution to property 6 only was I think 2.5 and minus 1.25. So this is definitely not either of those. And when I work out the Lagrange multipliers, what I get is I get 12 and 2. And each of these Lagrange multipliers is not the same as the Lagrange multiplier that we got when we had the problem, when we had each constraint in only as a single individual constraint. So let's take a look at the geometry and see what's going on. So for this problem, the shaded region is the set of feasible points. And what we see is the solution is on the boundary of the first constraint and is on the boundary of the second constraint. So it's on the intersection of the boundaries, and both of these constraints are active. Well, both of these constraints are active is indicated by the Lagrange multipliers both being positive, and geometrically, both of them being active means that the solution must be a boundary point of each individual constraint. And now this is a bigger point, is in general, the solution has to be a boundary point of the feasible set. And so what we've discovered is that when we apply both of these, both of the constraints were individually active. Together, jointly, they're active. And when they're both active, the solution is on the intersection of the boundaries of each one of those constraints.